Hello, everyone. This lecture, I'll be speaking about manipulating sum. So I'll take a few examples that were explained in the chapter 2 from concrete mathematics. So I think these examples are the most interesting and should show like a lot of like tricks that are used in handling sums and so on. So first, I begin with this summation. Then here. So here, so I'll just say a few properties first before we attempt to solve this. So like this, we already solved actually in the generating functions lecture. All right. So the first that we can actually rename the k here to any other variable. So this is equal, say s 2 for s. This is still the same. Also, we can have, so if we have some summation like this. This is a constant, so we can take this constant outside. So this a can be like a common factor. So it's like that. What else? So we can, and this s is not related to this, so just call this x, or just to avoid ambiguity. It's so just any variable. So then we can have also other things that we have an expression like this. So we have some summation over k. We have another summation over, say, s. And here we have some expression that depends on xk times the expression that, let's say this is another expression that depends on s. This we can write as, so we can see that here this xk is constant with respect to this inverse summation. We can take it as a constant outside. So basically we have something like that. Xk times the summation of s for y of s. And as we can see here, that this part here is a constant with respect to this summation, because here this value here doesn't depend on k. You can actually take it out. So after we take it out, we are left with something like that. So this summation is multiplied by this summation. As you can see, so the intuition behind this is that like here we go through all the pairs basically. So let's say, so this summation is defined for k that belongs to some set, and this belongs to some other set. So xk times ys. So basically this is Now we can say, for example, that A is 1, 2, and 3. And here the B is 4 and 5. So here we'll see that this summation is basically tries to make all the possible pairs from A and B. So here it's like x1, y4, x1, y5, plus x2, y4, plus x2, y5, plus x3, y4, plus x3, y5. So also this you can find is the same as we make a multiplication of the summations as we concluded. You can see this part here is if we make the product of these two equations, so the product has to happen by taking every member of here times every member of here. So basically it's another way of performing the Cartesian product. And actually this way we could use it later on in like counting on combinatorics, I mean. So we could also rename the iterators. For example, if we have something like that going from k whole 1 to n, or ak, this is the same. Like we can make so here we have the k is in this range, and we can define some variable s to be, I don't know, let's say n minus k, or n minus k plus 1. This will make it a bit simple. No, I will make it n minus k to, so the example would be better. So here we have this. So basically this inequality here, if we multiply it by -1, so we'll have that minus k. Like we all know, if we multiply by -1, we have to flip the inequality sign. So basically we have this, and then we add n. Here this will -1. Here when we add n, so end up having n minus k is then equal n minus 1, so basically our s. So our s lies within these values. So here we can make a substitution. Could be something like that. So here the s would go from 0 until n minus 1, and this would be a of instead of k, so we could basically n minus s. So it's this value here. Then we can make some renaming. So it's basically like that. So here I intended to rename it to the k, which was used here, and this is not ambiguous because here this k belongs to the summation. So here this summation, so if we have like two sets or something like that, of course this doesn't imply that ai equal b of I. Uh, so here it doesn't mean that uh, like we somehow making the terms equal, but here we just reverse the order of the summation. So basically this term is like a1 until an, while this other one it's just getting the same elements but in a different order. So it starts with an and we put k equals 0, and it will end up at a1 when we put the k equal n minus 1. So basically here, yeah, so this is this. And here the I doesn't have, like, can put it the same, and but we don't have to. If I intended to put it here the same to show that we can have like two summations of the same index, and we can rename the index of any summation as much as we want. We can actually make it the same, and then we can combine them in one summation. So this we might see later on. So back to the example, what I wanted to explain. We have Sn. So this example can also put the k is equal to 0. Like it doesn't matter what we put here. Can just make it 1 for simplicity. Okay, so this we can try to solve this summation in two different ways. The first is we take the last term out, so it would be something like that. It's exactly the same term plus the last term, which we didn't include here in the summation. So here we would have something like that. So this is the first equation we have for Sn. And then we can derive another equation, which is basically like that. So we'll try to deal with this expression here in a way that would reduce to some like lower term of this summation. So here, for example, I can say that Sn is equal to, so this k, I make it k minus 1 plus 1. So I end up having this expression, k minus 1 or k plus the same summation. So this is just a separation of this part. And then here I will divide all of this summation by 2 and then multiply again. So basically I'm taking a 2 as a common factor. So here I have from k equal 1 until n, k minus 1 or 2 times 2 to the power k minus 1 plus the same summation. So it's like that. And then this we have it. So here we can just increase the index, sorry, these values by 1, or increase the value of the index by 1. So here this same expression is basically equal to 2 with the summation k equal to 0 and minus 1 k to the power k. So here we have this. And as we can see here, so this, we can also make the k instead of 0 to be 1. And so this is basically 2 times Sn minus 1 plus this term, which is a geometric series. I will get later on how to calculate that. So we can also get a closed formula for that, but I'll skip this part for now. So here, this is, for now I just put the formula, and later on I'll explain how I got it. So we have this here. So basically it's equal to this. So this is Sn. And from this slide here, we can actually get like the value of Sn minus 1. So if we got here times 2 times n. So here this is, so Sn is, sorry, Sn minus 1 is equal to Sn minus m times 2 power n. 2n plus 1 minus 2. Then I expand this expression. Basically, this is Sn. So we find here that there's Sn. So I'll just take this part to here with subtraction, and all this term here I'll take it to the other side. So I'll end up having this. So Sn so basically this is a closed formula for the expression that we have. And just simplify it a little and do it that way. So here we can try to test this one out. So we can have k or k, then for k. And this k. So here if we start with 0, 1, 2, 3, 4. 1, 2, 4, 8, 16. Let's get another expression. And k times 2 to the power k, this is 0, 2, 8, 24, 64, and this 160. And sk is basically the summation of this so far. Here is 0, here's 2, here's 10, and 34, and 8, and 98, 858. And if we see this sequence here, n minus S0 is equal to -1 times 2 power of 1 plus 2, which is equal to 0. And S1 is equal to 0 times 2 to the power of 2 plus 2 is equal to 2. S2 is equal to 1 times 2 to the power of 3 plus 2, which is 10. S3 is 2 times 3 to the power of 4 plus 2. So this is 32 plus 2, so it's 34. Then we have S4, this is 3 times 2 to the power of 5 plus 2. This is 32 times 3, it's 96. Then we have 98, and so on. And we see it's matching the values that we got from when we actually tried to make the summation number. So this was the first summation, and you can see here, so at some point we did this, so there's this shifting. So this idea was used, but actually I didn't flip the sign, so here, this expression, notice, so the summation from k equal s until let's say from k equal a capital until b capital for a sequence ak. This is the same as we can shift it b minus a plus 1, a plus a. So we can always keep increase all the k in this part, in this sequence, I mean, but then we have to adjust the limits properly, and so on. So any substitution we are going to make for the iterator index here, for the k, we just have to make sure that it will get all the numbers that we got in the first time. Like we don't care about the order, so we can make basically any permutation here, but eventually you have to get the same elements that we add together. So as long as we do that correctly, then it doesn't matter what is the order of the iterators and so on, as long as it will get the needed elements. Okay, so then I jump to another summation. And here this is a multivariable summation, or let's say it's a 2D one. This. So here we have this, we want to make a summation of this value. So here we see we have like a 2D summation, and actually here we cannot swap them right away, because the inner loop depends on the variable of the first loops. So basically here we can just switch them. However, there's still a way to do that. So we look here at, let's say, if n is equal to 4. We have I and j. So I'll make a table in that. So the j go from 1 to 4, and the I go from 1 to 3. So basically here we will add something. So if I is equal to 1, we will come this position. Then if I is equal to 2, we'll visit these two positions in the j. And if I is 3, we'll visit these 3 positions, and if I is 4, we'll visit these 4 positions. So here we have like these positions are all can be put in this constraint that the I is greater than or equal j. This is equal n. So basically this constraint, when we try to find all the pairs I and j that satisfy this constraint, it will be all these pairs together. And it doesn't matter so how we iterate. So we can choose to fix the j first, like here, and find all the I, but here we have to find the i's that are bigger, and so on. So here if we choose 3, so we'll start the I from 3 and we'll go up, and so on. So here you can find that this constraint can be broken down into 2 constraints using this way. So one is that we use first the I as the outer constraint, and then use the j as the inner constraint. So here for the j, we have, since we already have the I that got used, so we have to put the j as the most tight constraint for this. So here the most tight is putting the j less than or equal to I. So this is if we start by choosing the I first and then trying to find the constraints for j. But we can also do it in a different way. So we can have that j, we can choose it first. So the most tight constraints that we can get if we choose the j first without knowing what the I is. So it would be to choose j between 1 and n, because this is the most tight constraints we can find without involving the I. Then in that case, we'll find that the I has the constraint between j and n. So these 2 constraints, if we mix them together, so they are equivalent. So like the conjunction of those 2 is equivalent to this expression. Also, the conjunction of those 2 is equivalent to this expression. It means that all the pairs that satisfy these 2 conditions are the same pairs that satisfy these 2 conditions, which are all these pairs that we drawn here in this table. So this helps us into like reordering this summation. As I said, we have here I is equal to 1. So this is the summation. So by using the constraints we derived earlier, we can actually write this as a sum for j from 1 to n. And then we have I from j until n. And this we have the value n minus j. So here we notice that this value doesn't depend on I, so we can get it out because it's a constant. So it's like that, n minus j times the summation I from j till n, where the function we sum is 1. So basically this term is equal to summation of j from I to n of this expression. And here this is the number of elements from j to n, which is basically n minus j plus 1. So we end up having this expression. Then I will use here the trick which I explained here. So yeah, this reverse trick. So here I will make a new variable, let's call it s, which is basically equal to n minus j. So here we'll find that this is from 1 and j to 1. So here the s will go from 0 until n minus 1. So this are the equivalent bounds for when you put this. And then I will also make it just in one step. I will rename the s to j. Basically here we have the new summation is going from j equals 0 till n minus 1. And here we have this j times j plus 1. Like, as you can see, the way I got this value, it's because this is actually equal. So if I didn't do the renaming, this would look something like this. Where this s is coming from here, as according to the definition, and also here. And we have the limits, as we could prove it here. But here I decided to rename it back to the same variable just to practice some, like, being fluent with the summations. And here now we can make this j equal 1. It doesn't matter that much in our case. So this is the summation for j squared. So it's the sum of squares plus the sum of the numbers until n minus 1. So these two summations have like standard forms to solve. So I'll just put them right now, and maybe later I could explain where they got from. So this is n minus 1 times n times 2n minus 1 over 6. This is the sum of squares. And then there we have n times n minus 1 over 2. So this is this sum here. So this is the value of the summation that we wanted to evaluate from the beginning. This guy. We can try to explain two more kind of easy examples. So here we want to have the what's called the geometric series. It's the summation for s from 0 to n, and we have some r to the power of s. So it's the summation of powers. So how can we do this? So we can do it in the same way that we solved the other summation for the first one I solved. So here we can just exclude the last element using this way. or here we can just exclude the first element. So this is 1 plus summation from s to 1 until n, or for s. Then I can take from here an r, this part, and r is a common factor. So we have this. Explain. And this part is basically 1 plus r times summation that starts from s equals 0 until n minus 1 of r to the power of s. Like this summation is just the same like this. I just shifted the s by minus 1. So as you can see, this is the expression for Sn minus 1, so according to the definition here, Sn minus 1. And here I will put this like this, this value for Sn minus 1 and get it from here. So this will be equal to 1 plus r times Sn minus r to the power of n. So this is equal to Sn. So if I expand this expression a bit, so we have r times Sn minus r to the power n plus 1. This is equal to Sn. So here when we rearrange, we have r minus 1 times Sn is equal to r n plus 1 minus 1. Notice here that all what I just used was just multiplications and additions. So until now, this formula would still be satisfied for the modular arithmetic. They would be exactly the same. But the next step, if we want to carry it out in modular arithmetic, we have to make sure that here we can divide by r minus 1. Basically, you end up having this formula for the geometric series. So this is the sum of the geometric series. So yeah, this is given with that or equivalently that r minus 1 inverse exists. So this is like the most abstract we can try to do. Then I can also make the arithmetic sum. Sn is the summation of all the numbers from 1 to n. So the way to do this is so here we can reverse the sequence in the same technique I used earlier. Say this. Here I'll make s is equal to n minus k plus 1. Where s is equal to 0. 0 or no, s starts from 1. And it goes up to n. And here we have n minus k plus 1. Sorry, n minus 1. So here I'll do a renaming of this. So it's k again. So this is equal to Sn. So if I add these expressions together, this should be equal to 2 times Sn. Basically, this is what we have. And here, since the iterators are exactly the same, so it's the k and it goes from both limits and both summations, we can take this in one summation and we add the terms inside. So it's k plus n minus k plus 1. So this we have that so this is the summation of k from 1 to n, and the term inside is n plus 1. So this term is a constant, we can take it outside. So it's the summation from k equal 1 until n of 1, which is basically n times n plus 1. So all of this was 2Sn. Basically, Sn is equal to n times n plus 1 over 2. Like as you can see here, there's a pattern that's coming. So here, the way that we could solve this Sn is by trying to find two different formulas for this summation here. So here we found this one, and here we found this one. This one. So basically, these two formulas, because there are two different formulas for the same value, somehow we could combine them to solve for this value which what we want. And here we can see we also did the same thing in the geometric series. So we got this first value for the geometric series. So it was one way. And the other way was using this formula. So it's two different formulas that also express the same value, Sn. So here we could use it to substitute for Sn minus 1 and basically solve for Sn. And you can see that this pattern got repeated in a few parts. So also this summation was the same, and so on. So there's a pattern that sometimes I used to be like in some way fooling myself, so I end up doing some derivation here for Sn. So I come with a really big expression for Sn. And here somehow I play with the equations a bit. So here there's some assumption I use. And here I played with the equations. So I got to some equations, then here I used some assumption A and B, and got at the end some equation. So sometimes these A and B are just equivalent to the same assumption. So I end up having here two expressions that when I subtract them, so they're equal to each other. And basically when I subtract them or use a substitution, I end up having the equation 0 equals 0. So this is basically means I actually didn't do anything different. So I just made one assumption, which is x, and I tried to somehow decompose it, but it was actually the same way. That was the same assumption. So here, when you meet like 0 is equal to 0, you know that you actually was assuming something simpler than it is. and you didn't actually solve anything. But yeah. Um. So maybe I would give a try. So I didn't prepare this example, but we can give it a try. So the sum of the squares until n. So here we can get the first way for this is doing this. So by excluding the last term, and then here we can. So the other way would be doing this. So we shift all the numbers by 1. Here we start from k equals 0 until n minus 1. And here I expand this expression. Okay, this one. Then I distribute this summation. So here's from k equals 0 till n minus 1. K squared plus 2 times k from 0 until n minus 1. The value k. And here summation of 1 from k equals 0 until n minus 1. So here we can see that this first part is actually s n minus 1, so the sum of squares, but until n minus 1. This second part is 2 times the sum of numbers from 1 until n minus 1, which we proved earlier to be equal to this. So this over 2, but then we have to multiply by 2, so this second expression is equal to n times n minus 1. And this third expression adds 1 for each of the values between 0 and n minus 1. So basically, it's equal to n. So here we can substitute with this Sn minus 1, put it here, so we end up having Sn is equal to n squared minus n plus n. And as you can see, this actually implies that 0 equals 0, so actually I didn't do anything. It's something I didn't intend. So how to solve this summation? Okay, so right now I actually failed to find some solution for this. How to prove the formula for it. Actually, you can also try this trick that we used earlier. I'll give it a try here. So it's the same Gaussian trick that we use for the symmetry. And so k squared. Basically, I'll make this substitution. So s is equal n minus k. So this goes from s equal to and the connection got bad again. So yeah, I'm sorry for this connection. So here I will go from k1 squared. So this I'll make the substitution of s is equal to n minus k. Then I'll make the renaming. So basically have this expression. So this is Sn is equal to n squared times n. Okay, let's make it a bit simple. So this is summation from k equals 0 until n minus 1. The expression n squared minus 2nk plus k squared. So when we expand this, we have n cubed minus 2n. So we make the summation from all the numbers here of k plus Sn minus 1. So here we substitute basically with the formula that we have. Minus 1. We'll divide by 2. So here we end up having the equation that we thought it was. So I actually still didn't write anything new here. So here we could somehow try to find some idea which might be useful. So using this expression here. So let's see if we do the following. We take the sum of cubes in k equal 1, and we still use the same trick. So k equals 0 to n minus 1, n minus k all cubed. So this expression is equal to k from 0 to n minus 1, n cubed minus k cubed minus k times n squared times 3 minus k times 3k squared times n. So this is what we have here. So we'll try to expand this. We have equals 0. So we call this, let's say, x capital of n. So here we'll have n power 3 times n. So this is the first expression, minus x capital of n minus 1 minus 3n squared times the sum of k from 0 until n minus 1. Okay, and then we have minus 3n times k from 0 to n minus 1, and here we have k squared. So this is basically xn. So actually this is how we solve the case for the we wanted to solve earlier. It's coming from, so this part we call it Sn. Here we have xn. Equal n to the power 4 minus xn minus 1 and 3n squared times Sn minus 1. Sorry, so I swapped just the last two terms, so this is actually something wrong here, so this should be a plus. This should be a plus, this should be a plus, and here we have 3n squared times n minus 1 over 2. So does this help us to find the xn or not? So, which basically yes. So, so okay, I'll try to expand this expression a different way. Again, hope this try to work. One, to the power 3. So this is n plus 1 minus k to the power 4. To n no, it's right now. The way I expanded, so it's from k to g of n minus 1 using this cube expression. So here's the summation from k to 0 n minus 1 for this expression, 2k squared, and this is 3k. So here, this is, we call this xn as we thought. So here xn is equal to xn minus 1 plus 3 xn minus 1 plus 3 n times n minus 1, which is the sum of all k, and here would be n. And here we also know that xn is equal to xn minus 1 plus n cubed. So I substitute this expression here. So this xn minus 1 plus n cubed. Basically here you can see, can cancel this with this to end up having this expression. It has all the numbers known except here we have the Sn minus 1. So basically we'll have something like that. So 3 times Sn minus 1 is equal to n cubed minus this expression, which is 3 times n minus 1 over 2. Minus n. So basically this is the form for Sn minus 1. I can try to simplify it a bit further. So we can do this. I just copy it here and then put it in. Just like that. So here I will substitute every n minus 1 with n. Basically this is, and just do it like that. 3 n 1 2 n. From this here, actually I'll just take the n plus 1 over 2 as a common factor. N plus 1 over 2. To end up here having n plus 1 all squared times 2. Here minus 3n. Here minus 1. So this is if we expand the expression, so end up having here we have 2n squared plus n plus 1. Sorry, I'm actually wrong here. So this is minus 2, minus 2. So this is okay. N plus 1 over 2. So if we divide those by 3, so here I'll take an n as a common factor, and I will divide by this 3. So we will basically end up having this formula, which I use sometime in this one. Okay, so this was a bit unstraightforward, but yeah. So as we can see that in order to compute the sum of squares, I had to somehow try to compute the sum of cubes and then make this shifting by -1 idea. So, and then I ended up having some expression that includes only the sum of squares. Actually, this method can be generalized to if we want to make the sum of cubes. So basically, we try to find the sum of a to the 4, and we will go like that. We expand this expression, so maybe like that. Here n-1. So basically, we call this now Zn. So here we have Zn-1 plus 4 times xn plus 6 times Sn plus 4 times, so these are n-1, n-1, and here the sum of numbers, and here, so the sum of, like the power of one of the numbers. Here we have n, and here we substitute for the n-1, so n for 2. So basically here it's the same trick, so we take this out of this, and here we have an expression for xn-1, which is the sum of cubes, and it's all representable in the sum of squares and sum of linear numbers and so on. And so we can basically try to find this xn-1, and it has a formula indeed. So the last thing I'll talk about an infinite summation. So I'll just take an example just because it's an interesting one. Basically, it's the sum of all the powers of 2. Okay, let's recall first the geometric sum, so the geometric series. So this was equal to r to the power n plus 1. So it's like that. And so if n goes to infinity and r is provided, so r is less than 1, absolute r is less than 1. So for this number, when we keep multiplying it times itself for infinite times, this will be equal to 0. Basically here this infinity is equal to 1 minus r. So this is the main condition that we can use this expression. However, we can just try to violate this condition, and we put r's to be equal to. So we have the summation of all the powers of 2. So this actually turned out to be equal to -1. Here, this, even though it's like unintuitive, so it shouldn't be correct, this form. However, there was a really interesting observation that Donald Knuth said in the book about this. So we can actually think of this number as if it's so this is the powers of 2. So if we think of this number here, the binary representation, so each of those adds to the ith bit. So basically, the 1 adds to the 1 to the first bit, and the 2 adds 1 to the second bit, and 4 adds 1 to the third bit, and so on. So it's a number that's represented like that in the binary. So actually, this number is somehow we can think of it as the 2's complement that we have for the -1, but in infinite binary representation. So as we know, like we have, for example, in computer science, when we use so some signed integer, so -1, for example, we represent this in the 2's complement, which is basically we flip the bits of the 1 and we add 1. And so we end up usually having all the expression all ones for all the bits that we have. And so here the binary representation we have is in infinite bits. So actually this number would be equal to -1 because it's the 2's complement of the -1. So this was just an interesting idea that I came across in the book. So yeah. And also there's something it would be nice to mention. Okay, so there's this trick which I used to try to compute this summation point. So the sum of numbers, and basically I did this by shifting S3, and I added these values, so they ended up to be equal 1/2 of n plus 1 S3. So this trick, it was used by Gauss when he was really young. So as far as I remember the story, he was like maybe like 14 or something, and he was sitting in a class, and there was a teacher who wanted him to give him an exercise so he can take long time to solve it. So he gave to Gauss like solve this summation until 100. And he thought it would take a long time for him because he would try to make a summation of 100 numbers, but then like Gauss found this like symmetry trick. So he basically made the same summation, but like flipped like that. Basically here it has 1. And basically if you add each number to its corresponding pair, so you end up having 101. and this number is occurring 100 times. So basically this summation, we call it S, then we have 2S is equal to 101 times 100, which is, so when we divide this by 2, we get so this idea is called the Gaussian pairs. So we have these pairs that could be formed with symmetry. So yeah, this was called a Gaussian pair. So it was just an interesting story that I thought I could share. And yeah, just to introduce the name for this trick, because I used it earlier and I think some people might encounter it in different parts, so I thought it would be good to know the name. All right, so that's it for today, and I hope this was beneficial for you, and thanks for watching.